Hello everyone. In this chapter, chapter 20, module 4, we will be covering a new field, is the magnetic field. Up until now, we have been covering the subject of electric field and electricity. In other words, electrostatics and electricity, where you have a charge that is in a static situation, is not moving, and then there is a field associated with it. And then later on we discussed when charges are in motion, which basically you have a stream of particle like an electric current. Now we move to a completely different subject, and that is the magnetic field. Basically the course that you've taken is electricity and magnetism. So we finished the part of the electricity, now we move to the magnetism part. So the subject is magnetic field, and we have a couple of chapters in the book on that. But this chapter, chapter 20, is a large chapter in terms of concept. The number of pages are basically the same as the number of pages of other chapters, but the concepts of the magnetic field is a little bit more abstract, especially for those who have never taken physics before. So I decided to divide the chapter into 2 weeks, and I will be doing 2 videos, part 1 and part 2. In this part 1, I will be covering the magnetic force and the magnetic force due to a moving charge, and the magnetic force due to a current. In the next video, which hopefully I will publish it in the next couple of days or so, it's going to be about Ampere's law, and then if I have some time, I would do some problems on the homework. The homework that you have this time is a little bit larger. I think it's around 10 or 11 problems, homework problems. Because, like I said, because there's just too many concepts in the chapter, and I wanted to cover all of them. But the good news is that you have 2 weeks to finish all of that. Okay. All right. So let's dig into it. So when we say magnetic field, the magnetic field is slightly different in behavior, how it behaves from the electric field. Let me give you just a kind of a little comparison between the two. Electric field, when you think of electric field, you would think of straight lines like that, electric field lines that are going from the positive terminal to the negative terminal. Instead of saying, if you have a positive charge, the electric field lines are out of the body of the charge like that, and if it's a negative, of course, it's inward. We did that before. Okay. For the magnetic field, however, there is some similarity in that sense, and that is that's the negative charge. For a magnetic field, imagine you have a bar magnet. Okay, here is a bar magnet. As you know, the bar magnet has a north pole and a south pole. Here is, let's say, the north pole is here. Here is the south pole. And there is magnetic field just like in the electric field, but those magnetic field lines are curving. In other words, they come out of the north and they go into the south, instead of saying like that. In other words, it is the magnetic field needs a source and a sink. A source where the magnetic field come out of it, and then you have the sink where it have to go into it, instead of saying. And that source and a sink is that the south is the sink and the north is excuse me, did I say the south is the sink and the north is the source? You get that? So it will be going from the north into the south like that. Where for the electric field, you have an electric field that is, let's say you have a positive charge like this one here. It doesn't need a sink. In other words, I have this positive charge. Let's say I take out this negative charge. You could have an electric field just going to infinity. They just extend to indefinite distances without it needing to sink into a negative charge. You see what I'm saying? That's the main difference. That's one difference between them. Another difference is that if you have an electric field, here's electric field, and let's say this is positive, this is negative, and of course go in that direction. So the electric field is going from, left to right. So if I have a negative charge here, okay, so what's going to happen to the negative charge? It's going to be attracted to the positive terminal, if you will, right? However, if I have a positive charge, it's going to be attracted to the negative terminal. So here is the force, if this charge, let's say call it Q, and this one Q. So here's the force. So basically here, as you can see, the electric field is parallel to the force, or it can be anti-parallel to it. In other words, an opposite direction. You see what I'm saying? So it's either parallel or anti-parallel, depending on the sign of the charge. However, if I have a magnetic field, what will happen is that if I have a charge and it's moving at a certain velocity, the magnetic force on that charge, it's not going to be parallel or anti-parallel. It will actually be perpendicular. Okay, so here the motion is the influence on the charge due to the magnetic field is going to be in the perpendicular direction. I'm going to talk about that later in the lecture when we go into the right-hand rule. I'm going to show you a video on that. But that, for now, just understand that the electric field and the force are either parallel or anti-parallel to each other, always, on the charge. But in the magnetic field scenario case, the magnetic force acts in a perpendicular direction to the magnetic field. Okay, more on it later. Okay, the symbol of magnetic field, we refer to it as big or capital letter B, and it's a vector, so we have a vector sign on top of it. And the unit of the magnetic field is the Tesla. I'm going to put it in bracket. Okay, and the symbol of the Tesla is big T. Okay, the Tesla, just like the Coulomb, is a very large unit. So most of the time you're going to see nanotesla or millitesla and so on. Okay, always be something, a fraction of 1 Tesla. Because the Tesla itself is a very large unit. This is of course in the MKS system, SI MKS system of units. In the SI CGS system, another unit that is used is called the Gauss. And the Gauss is 1 Tesla is equal to 10 to the 4 Gauss, 10 to the 4 G, okay? Well, basically 10,000 Gauss. So the Gauss is much smaller of a unit, magnetic field unit, than the Tesla. But the one we're going to be using in our book, and the one that is, I believe it's more common, more popular, is the Tesla. Okay. An example of that, as you know, the Earth has a magnetic field, and the magnetic field of the Earth, B sub Earth, is about 5 times 10 to the negative 5 Tesla, or 0.5 Gauss, if you will. Okay. So what happens when you have a charge that is moving in the middle of a magnetic field? This is the subject. This is the first topic that we're going to be covering in this video. Here's how it works. Imagine I have a plane. There we go. Say the XY plane or something like that. And let's say I have a positive charge. Let me put the XYZ. So here is the, try to make it as straight as possible. Here's the x-axis. Sorry, that should be the y. Here's the y-axis. Here is the x-axis. And then let's say here is the z-axis. Remember, the z-axis is out of the plane above it. Okay? And And let's assume that I have a positive charge here. There it is. Okay, and this positive charge, let's say it's moving along the x-axis in this direction. Okay, that's a positive charge Q. Okay, and let's assume there is a magnetic field on the plane, and this magnetic field is along the y-axis like that. This is the magnetic field B. Got it? So what will happen if the charge is moving into a magnetic field? Okay, in the middle of a magnetic field, what will happen? There will be a magnetic force on that charge. This magnetic force will act in the perpendicular direction, or rather perpendicular to both the magnetic field vector and the velocity vector. And it's going to act, for this case, V cross B, and it's going to be, in this case, in this direction. By using the right-hand rule. Unfortunately, I cannot show you my hand. This is a screen reader. The program that I'm using is a screen reader. I cannot show you my hand, but I'm going to show you a video on how to use that, or at least direct you to a bunch of videos. So let me pause here. I'm going to go to the YouTube. I already prepared that page. If you go to the YouTube and type in magnetic field right-hand rule, and you'll come with a bunch of lots and lots of videos on how to use the right-hand rule. Please take the time to learn it. Okay, unfortunately, we're not in a classroom setting where I can show you and even hold your hand and show you how that works. So you need to watch the tube. Some of those videos are available. One I would recommend is this video right here by this gentleman, Bozeman Science. He has a bunch of videos that are very good. Let me just show you a glimpse of it. Again, you can watch.
Just a second.
Commercial. Hold on.
What's your favorite browser extension?
Online shopping.
There we go.
There's no magnetic force. But as it moves, it has a velocity vector. And if you're ever moving as a charged particle through a magnetic field, then you're going to have a force applied to you, and we call that the magnetic force, or F sub m. Now, things that you need to remember is that it's a perpendicular line between the magnetic force and the velocity, and it's also perpendicular between the magnetic force and the magnetic field.
They're actually mutually perpendicular. V, B, and F, the velocity, the magnetic field, and the force are always mutually perpendicular to each other. Okay. Anyway, I'm not going to have you watch the whole thing, but let's just go on.
Velocity vector and the magnetic field vector don't have to be perpendicular to each other. How do we calculate the magnetic force? Well, there are only three things that really deal with that. First one is going to be Q. That's going to be the...
I'll stop here. There is a commercial about to come. I don't want to waste my time with that. But please take the time to maybe watch this video or others, whatever one you feel comfortable with. This one is called the Magnetic Force, and his channel, Bozeman Science, I believe that's his name. Bozeman Science, and he has other videos that I find them to be helpful for you. Maybe not. But anyway, okay, let's go back to the video. Okay, so with this in mind, if I want to calculate this force, okay, so we said that if I have a charge moving with some velocity in one direction, and then you have a magnetic field perpendicular to it in another direction, okay, x, y, z, for example, the force vector, the magnetic force, is going to be in that third direction. You got that? And I mean, it's not downward, it's upward. Why is it not upward? Why is it not upward, but it is downward and so on? The reason is because you have to use the right-hand rule. Okay. So anyway, this force F is equal to QVB sine the angle between V and B. Okay, there it is. Let me explain it to you. I'm going to do a bunch of problems. If this is too abstract or too difficult for you, that's okay. I'm going to do a bunch of problems just to show you how this works. But basically, the meaning of it is the following. If I have, let me draw another picture. Something more specific. Again, let's just go back to the same plane. Here is let's just do it the same way. So we have here y, this one is x, and this is z above it, right? It's coming out of the plane like that. Here's z. And again, let's assume this is the positive charge right here, q. Assume that the velocity, let's say it's moving in this, the particle is moving, let's say, in this direction, say at 45 degrees or something like that between x and y. And let's assume that the magnetic field is in this direction. You see that? In other words, there is an angle between them right here, okay? Let's make it 45, for example. Got it? So in this case, there will be a force, okay? There will be a force on that charge, and that force is going to be, it will be equal to q, the amount of the charge, times the velocity, times the magnetic field intensity, sine the angle between them, which happens to be 45. You got that? Okay. This is actually the example on page, or example 20.1. Let me go to it. Let me show it to you in the book. Page 640. 640. Right here. I make it a little bit bigger. There we go. What you have, look at the picture. It's pretty similar to the plane. Oh, okay, he's using 30 degrees rather than 40. But anyway, so in this example, we will calculate the force on a proton moving in the magnetic field. Okay, the magnetic field is along the z-axis. He has the different set of axes. Anyway, so there is a z-axis right here. So we have a proton moving along the z-axis. A beam of protons moves through a uniform magnetic field of magnitude 2 Tesla. Okay, so B here is equal to 2 Tesla, which is very intense. That's probably in a physics lab or some professional lab. 2 Tesla directed along the positive z-axis. Okay, the protons have a velocity of magnitude 3 times 10 to the 5 meter per second in the xz plane at an angle of 30 degrees to the positive z-axis. Okay, so what's important is the angle between V and B. Okay, in other words, if he gives you the angle between V and X, you have to get the angle between V and B. Okay, it's always between the two vectors, V and B. Okay, so he gives it to you already, so you don't need to calculate anything. It's 30 degrees to the positive z-axis. Find the force on the proton. Okay, find the force on the proton. Oops. And the charge of the proton is given by, of course, as you know, it's the fundamental charge. So let's do this problem. Example 20.1. I'll make a drawing very quickly, just a quick sketch. Here it is, and I'm copying it from my hard copy right here. So here is the a proton. Here is the, what's axis is that? That's the y according to him. This is the z. This is the x, and this is the b, the magnetic field, that is. The velocity is like that. Here is the velocity. Here is the angle, theta. I'm going to call it theta for now. So he wants the force, right? That's what he said. He said, find the force on the proton. Okay? So we know that the force, F, is equal to QVB sine theta. Just plug everything in. Of course, in this case, because the proton is a fundamental charge, I can write it as E. EVB sine theta. So far, so good. E is, of course, is the fundamental charge, 1.602 times 10 to the negative 19. Multiplied by the velocity, he gives it to us. It's equal to 3 to the power of 5 times the magnetic field. I believe he said 2 Tesla. Again, this is a very, very large, very intense magnetic field. Okay, in a professional lab like a nuclear physics lab or particle physics lab, usually it's around 2, 3, 4 Tesla. Okay, that's astronomical, really. It's a huge, huge number. So anyway, so we have a 2 Tesla and multiplied by sine 30. Sine 30 is half, and then you just do the calculation for that. Instead of saying, And I'm sure he did it the same way. Here it is. He called it sine phi rather than theta. Doesn't matter. There we go. And then you just calculate that. And then the force would be 4.8 times 10 to the negative 14. So it's 4.8 times 10 to the negative 14 Newton. Same thing, right? I mean, forces are all in Newton. And there we go. That's how you calculate that. Okay? Simple? Okay. I'm going to come back to this velocity selector in a minute. I want to do one more problem. Let's see, look at my notes here. Oh, yeah. We have something very interesting. It's called the Mass Spectroscopy. And that's a section, a whole section in your book. It's section 20.4. Please take the time to read it. Section 20.4. It's more of an application to what we have just said, what we have just talked about. Okay, it's called. He calls it Mass Spectrometer. Spectrometer. Okay, what is a mass spectrometer, or the science of mass spectroscopy? Mass spectroscopy answers the following question. As you know, the mass of the electron, 9.11 times 10 to the negative 31 kilogram. Mass of the proton, what is it? 1.602 times 10. Sorry, it's not that. It's 2.78. Is that right? 2.78. 1.67. Sorry, 1.67 times 10 to the negative 27, and so on. Okay, or maybe mass of the oxygen atom. Okay, or mass of the helium atom, and so on. All the masses in the periodic table, for example. How do we know all these masses? I mean, have you thought about that? I mean, how do you know? Obviously, we're not going to take the electron and put it on a scale and measure its mass. You see what I'm saying? So there is a way to do that, and this method of measuring really tiny masses like particles, subatomic particles, is a science called mass spectroscopy, or a device called mass spectrometer. We're not going to study the device, but I'm only going to show you the concept behind it. And the concept involves using a formula very similar to the one here. Okay, here's how it works. Let me erase all of that. Imagine I have an electron or a proton gun. What does that mean? Imagine I have a capacitor like this, okay? And let's say this is the negative side, this is the positive side, okay? And let's say assume that I'm interested in finding the mass of the proton. All right, we already know what it is, 1.67 times 10 to the negative 27. But let's assume I don't know that. I want to actually do an experiment to find the mass of the proton. How do I do that? Here is how it works. First, I generate the proton, and I put it, I come up with the proton, and then I put it inside the capacitor like that, right here. So what's going to happen? Well, the proton is going to be attracted, this proton is going to be attracted to the negative plate, correct? So what's going to happen to it is going to shoot toward the negative plate because it's attracted to it. So far, so good? So it's going to go with a certain velocity v. Of course, if I would intensify the voltage here, delta v, we talked about that before, it's going to go faster. You see what I'm saying? So anyway, by the time it comes here, let's assume there is a small hole here, right here, there is a hole, so the proton is going to come out of it like that. And right here in this region, to the right here in this region, assume there is an intense magnetic field here. And this magnetic field, let's assume it is into the page, the direction of it is into the page, like that. So across means into the page. Please remember that. Cross means into the page, into the screen, whatever. And this one, dot, is out of the page. You see what I'm saying? So this is like right, left, right? Up, down into, out of the page, out. Oh, I reached the limit of the screen. There we go. Into, get that? There we go. Okay. So let's say that we have this intense magnetic field, and it is directed into the page. Okay. So what's going to happen? Here is the proton. It's going to come out here, come out of the capacitor with very large velocity. So now it's going to enter the magnetic field like that, right? Again, let me just clean it up because I want to draw the diagram of this thing. So what's going to happen to it? The force, see, the magnetic field is into the page. Here is the velocity vector. If I use the right-hand rule, the electron, or excuse me, the proton is going to follow a circular path like that. And it's going to hit this side right here. Assume that I have a photographic plate here, and I would see that. And then let's assume that I'm able, so it's going to follow a circular path like that. Here is a circular path, okay? And that circular path, I can actually measure it in the lab. I can measure the radius of that circular path. Got that so far? Okay, so what happened here? The reason it follows a circular path is because of the nature of the magnetic field. Particles always move in a circular fashion once they are immersed into the magnetic field. Okay? So, because of that, so if I take the proton in its path, let's say if I take the proton right here, here's the proton, while it's following a circular path. So here is the radius, right here. So it's moving with this velocity like that, right? And this is the centripetal acceleration, or if you will, the centripetal force. Well, the centripetal force here is basically the magnetic force. And as we know, F equals ma, this is the force on this proton, and the nature of this force is the magnetic force, which we said what is equal to QVB right there. Of course, if theta is 90 degrees, which is the case for us, so sine 90 is 1. So there is no need to write sine, just QVB. Okay. So here I have QVB equals to the mass of the proton, that's the one I'm looking for, times times the acceleration. But this acceleration is what? It's a centripetal acceleration, because it's a circular path. What is the centripetal acceleration is equal to? It's equal to v squared over the radius. V squared over r, if you go back to our physics 151. So now I have this interesting relationship. This v and this v cancel out. And I want to solve for the mass, because I'm interested in the mass of the proton. So if I calculate that, so I go QBr over v, and there we go. I have an expression for the mass. And that's how I know the masses of all the subatomic particles, or any atom in the periodic table or in the nuclei chart. It basically, all I need to do is to know the charge on that particle, the intensity of the magnetic field that I'm preparing in my lab, the radius of the path, which I can find out easy, okay, and the velocity of that particle when I prepare it to go through this, say a capacitor, a parallel plate capacitor. So if I know all these, I can immediately find out what is the mass of that subatomic particle or ion or whatever it is. You see what I'm saying? So it's an interesting technique. It's been practiced in the early part of the 20th century, and that's why we know, that's how we know about all the masses of atoms and ions and subatomic particles. A very, very important technique. Okay, good. So keep that in mind, and I hope you understand how this was derived through the diagram here. Let me do one problem from the book. I'm going to do example 20.2, but before I do it, page 43. Right here. But before I do it, I want to tell you about what is called the cyclotron frequency. This is, I believe, the previous page. This is the equation that we have just derived. He only solved it for R. We solved it for the mass. You see what I'm saying? So this one gives you the radius of the circular orbit in a magnetic field. Okay, and then you have what is called the cyclotron frequency. It's not really important to know the details of that, but I'm just gonna derive for you how it is derived. It's only basically one more step to what I have just done. So let me just go. So we arrived at this relationship right here for the mass. Let me solve for the radius since he's solving it for the radius. So the radius in this case is going to be equal to mv over qb. That's what he has here, right there, right? He has a absolute value on the q because he's just telling you don't put the sign of the charge. That's all. Anyway, so there we go. Now the velocity here, as I told you, it's basically the velocity around the circular path, which is the same as the velocity when it comes out of the parallel plate capacitor here. Okay. Now we know that because this is going in a circular fashion. What is the angular velocity? In other words, it's going around in a circular fashion, so I can say what is the angular velocity. Angular velocity, if you remember, is the omega. Omega is equal to v over r. In other words, the velocity is equal to omega r, if you remember. Okay, so I can plug this into the formula because I want to solve for the omega, angular velocity. So in this case, r is equal to m omega r over qb. Notice that the r's cancel out, and if I solve for the angular velocity, it will be equal to qb over m. You see that? And this is basically the equation that he has in here. There it is, qb over m. And that's, he calls it the cyclotron frequency. A more useful formula, however, again, if you remember, omega is equal to 2 pi f, f being the frequency, right? Remember? And so I can substitute this into this equation. So I'm going to have 2 pi f equals qb over m. So now if I solve for the frequency, it's going to be equal to qb over 2 pi m. Okay, that's another useful formula, or this is the one that I'm familiar with personally, is that the cyclotron frequency. This is more, I don't know, maybe this is more popular, but the cyclotron frequency is qb over 2 pi m. And that leads us to the next example, which is example 20.2. Let me show it to you where we will be using this formula, I think. Let's go to it. And in this example, it says a magnetron in a microwave. This is like a little device in the microwave. A magnetron in a microwave oven emits microwaves with frequency 2,450 megahertz. Okay, let's work on it. So we have the frequency is 2,450 megahertz, a million hertz. Okay. What magnetic field strength would be required for electrons to move in circular path with this frequency? Okay, for electrons. All right. So we have the Q here is the charge of the electron, which is the fundamental charge, 1.602 times 10 to the negative 19 coulomb. Okay, and so he's asking for what would the magnetic field strength. He wants the magnetic field B. See what I'm saying? Okay, all I need to do really is just plug it in here. You see what I'm saying? Simple, really. Oh, I already know what the mass of the electron. The mass of the electron is 9.11 times 10 to the negative 31 kilogram. And it becomes really a trivial problem. You just plug it in. So in this case, the magnetic field B, I'm just looking at it and cross-multiply it in my mind and then just get the answer. So that's going to be 2 pi m f over q, which is E. There we go, right? And then you just plug in everything. That's going to be 2 pi, which is 6.28 together. Mass of the electron, 9.11 times 10 to the negative 31. Times the frequency, he gives it to me already, 2450 times 10 to the 6 hertz, right? Mega is a million, divided by the fundamental charge, 1.602 times 10 to the negative 19. And then we calculate that. I believe he did it the same way, I hope. Slightly different. He solved for omega first, and it doesn't matter. Anyway, so when you solve for it, as you can see, it's a very small number. You will get 0.08. Let's believe that our calculation is correct. So it will be equal to 0.0877 Tesla. Still a large or intense magnetic field. Okay? All right, good. Let me move on to the next topic, and then after that, I'll do some problems from the homework. You see what I'm saying? The next topic is kind of a continuation of what we have just studied. And the topic is section 20.5. Let me show it to you. Page 645. Oops, 45. There it is right here. It said the magnetic force on a current carrying conductor. What's he basically saying? The magnetic force on a wire. Okay, and the wire is live. It has a current inside of it. That's really what it means. Okay, so magnetic force on a wire. Okay, now what's the difference between what we have just studied and what we are going to study? Is that what we have just studied is that the magnetic force on a charge, moving charge. That's it. So what is the magnetic force on a moving charge? Magnetic force on a moving charge, F equals QVB sine theta. That's it. That's basically the answer. You see what I'm saying? Now, magnetic force on a current carrying wire. So magnetic force on a current carrying wire is basically equal to F equals to ILB. Okay? ILB. Now, what is I, L, and B? Sine theta, sorry. Okay, here it is. Imagine you have a current. Here is a wire, a segment of the wire. You see what I'm saying? Here's a segment of the wire. And the current, let's assume, is in this direction. And let's say, hypothetically, that the magnetic field is into the page. Okay? If you use the right-hand rule in this case, there will be a force on this wire that will literally lift it up. It will hover in space. This is magnetic force. I'm going to call it F sub B, B here for the magnetic field. Okay? It will actually hover in space like that. You see what I'm saying? Let me show you how that works. I'm going to do example 20.4. Kind of a nice example. I like this example. And that's on page 647. There it is. So you have this bird right here. It says, in this example, we will incorporate a magnetic force on a wire into a static equilibrium problem. He said the world's lightest bird is the bee hummingbird, its mass is 1.6 gram. Okay, that's really, really, really light. Less than a penny. Well, the penny is about 3 or 4 grams, so that's probably half a penny. As shown in the figure, there it is right here. We design a perch for this bird that is supported by a magnetic force. Okay, so imagine that this perch, basically a wire, okay, and then you have a current going through it. Do you see those current guys? Okay, and then of course the bird is standing on it, and the bird has a weight, so it's going to be pushing on it with W. That's the weight of the bird, right? And remember, the weight, the bird has a mass 1.6, so it has a weight, right? And then, but because the wire here, and we have some external magnetic field, it will cause it with it will cause a magnetic force to be moving up. But let's continue reading. As shown, we design a perch for this bird that is supported by the magnetic force. The perch is 10 centimeters long and has a mass of 7 grams. Okay, that's the mass of the perch, and contains a wire carrying current of 4 amps. Okay. The perch is oriented at right angles to the uniform magnetic field and is just strong enough to support the perch and the bee hummingbird. What are the direction and magnitude of the magnetic field? Okay, so let's find the magnitude. I mean, the direction here requires that you have to do the right-hand rule. So how do we do this problem? Here's how it works. So here is the bird. Let me draw a bird. I think I can draw one. Got the tail here. There we go. Smiley bird. There we go. And here's the legs. Here's the perch. Right there. And let me put the forces on it. First thing, you have the mg of the bird, the weight of the bird, right? Like that. We have the current going in this direction, and then you want the magnetic field to be upward because you want it to balance with the weight. See what I'm saying? So here you have the balance here with, well, how many weights do you have here? We have 2 weights. We have the weight of the, here's the perch, sorry. Okay, so here we have 2 weights. We have the weight of the bird plus the weight of the perch. I'm going to call it M sub PG. Okay, so we have 2 of them, and those are going to balance with the magnetic force. So F sub B. Let me put it properly in terms of Newton's second law. Sigma of F equals 0. You know, the equilibrium thing. So that's going to be F sub B must balance with the weight of the bird plus the weight of the perch. There we go. And you can just go like this. MB plus MPG. See what I'm saying? And the magnetic force here is going to be what? Remember the formula? Because you have a current. And of course he said the perpendicular. So sine theta, sine 90 is 1. In this case, just ILB. L here is what? Is the length of the wire. Maybe I forgot to mention that. I'm sorry. L here is the length of the wire. I is the current. And B is the magnetic field. Okay? So in this case, I will have ILB, ILB. And he's asking for B. So it's just going to be MB plus MPG divided by I times L. I got everything. I can just, plug in the numbers. But let me clean it up a little bit. He said the mass of the bird is 1.6 gram. That's 1.6 times 10 to the negative 3 kilogram. And the mass of the perch is, I'm reading it from my hard copy here, 7 gram. So that will be 7 times 10 to the negative 3 kilogram. Okay. So we add them up together. So it's going to be, 8.6 times 10 to the negative 3 times 9.8 divided by the current. He says the current is equal to 4 and the length is 10 centimeters. You see that? So here we have the current is 4 amps, and the length is, I forgot already, 10 centimeters, 0.1 meter. And there we go. We just solve for that. And when you solve for it, you're going to get 0.2 Tesla. And it turned out that the magnetic field is into the field. Again, you want to use the right-hand rule. It's into the field, into the page, excuse me. Okay? Okay, good. Oh, by the way, the next section, 20.6, let me show it to you very quickly. There it is, force and torque. We're going to skip that, okay? So please skip force and torque on the current loop. I don't cover it, so we can just kind of skip it. The one that, the next section, the magnetic field of a long wire, Ampere's law, that is, which is section 20.7. That's, of course, a requirement, and we will be talking about it, and the rest of the chapter, that will be in the next video, okay? So for now, that's all we have. So I am done with the content that I wanted to cover, in brief, though. But I'm going to be doing at least maybe 3 problems or so from the homework. So let's start on working on those. Let me start with problem number 11 in the textbook. Let me go there. Oh, I know the page number. There's no need for that. It's on page 664. Like I said, you have about 10 or 11 problems. Okay, 11 right here. He says, a velocity selector, I'm going to tell you what that means in a sec. He said a velocity selector having uniform perpendicular electric and magnetic field as shown in the figure. Okay, this yellow, those 2 bars is a velocity selector. It's not a capacitor. Kind of similar to a capacitor, but it's not quite. Excuse me. The electric field is provided by 150 volt DC battery. There it is right here. Connected across 2 large metal plates that are 4.5 centimeter apart. What must be the magnitude of the magnetic field so that the charges having a velocity of 3.25 kilometer per second perpendicular to the field will pass through undeflected? Okay, sounds like a really tough problem, doesn't it? B, show that the magnetic field should point in the region between the plates. Again, this is the second part. You need to know the right-hand rule. Please take the time to learn the right-hand rule. All right, so how do we solve a problem like that? First of all, let me explain to you. Well, let me explain to you what a velocity selector is before I do that. All right, a velocity selector imagine you have 2 parallel plates, just like a parallel plate capacitor. Excuse me. Here is one right here. I'm going to make it a little bit thicker than usual. There they are. And then you have another one here. They have the same thickness, okay? Ignore my drawing here. And let's assume that this is a positive terminal, positive plate, whatever. This is the negative one. As you know, and both have the same charge, right? I mean, the same the same charge. So in this case, as you know, there will be. Let me use different colors so make it look pretty and clear. So in this case, you will have a electric field going in this direction like that, from positive to negative like that. That's the electric field. Okay. I'll put an E here for electric field. Okay. Now, one more thing. What I'm going to do now, I'm going to shine a magnetic field into the page. Okay. So I'm going to also shine a magnetic field, not just electric, but also magnetic field. So let me put it in blue, maybe. So now we have a magnetic field into the page like that. That's into, right? I don't want to put too many X's in the middle because I don't want to clutter it, but let's say that it's everywhere. So here you have two fields, electric field and magnetic field. Both are perpendicular to each other. As you can see here, the electric field is going from right to left, and then you have the magnetic field is going from into the page, okay, and they're both perpendicular to each other. Now imagine I take a particle. Let me go back to black color. I have a particle. Let's make it positive right here. I'm going to put it into this mess right here. Here is the particle of some charge q, and I'm going to shoot it with some velocity this way. So what's going to happen to it? Which direction is going to go? Okay, the velocity selector basically, as the name implied, it selects certain particles with certain velocities, but that's not our concern for this. The problem, or even for the chapter that we're studying. Basically, what we are concerned about is that how is the velocity is influenced by both the electric field and the magnetic field, or the motion. Okay. Now, imagine the particle here. Okay. Here it is, the same particle. Let's say it's right now. It's here, and I asked the question: what are the forces on the particle? Ignoring the weight. Okay. The particle is very, very tiny. The gravitational effect is not there. What are the forces on it? Well, there are two. Because you have an electric field, so there will be a coulombic force. You see what I'm saying? And that coulombic force, of course, the particle is positive. That means it's going to be attracted to the negative terminal right here. You see what I'm saying? So in this case, it's going to have, let me just delete this cross right there. There we go. So it's going to have an electric or a coulombic effect, so coulombic force going in this direction. Let me call it E here. Electric force. You see what I'm saying? Because it is attracted to the negative terminal. It's a positive particle. Another one, because it is in motion. See, the particle is moving. And we said that in the beginning of the lecture. Whenever you have a charged particle with charge Q in motion, there will automatically be on it a magnetic force. Motion moving in the midst of a magnetic field. So there will be a magnetic force on it. Using the right-hand rule for that, and you will find that this magnetic force is going to be in this direction. Let me erase this. It's going to be in this direction. So now you have those two forces on it, okay? Now what I'm going to do is the following. I'm going to tweak or fine-tune, that's probably a better term, fine-tune the velocity selector in such a way that to make VB and VE to be equal. Why do I want to do that? Well, think about it. If the electric or the coulombic force is stronger than the magnetic, what will happen to the particle? It's going to curve down to the negative terminal like that. See what I'm saying? Now, if the magnetic force is stronger, it's going to curve down to the positive terminal like that, for example, because the magnetic force here is stronger than. So so what I want to do, I want to fine-tune it in such a way that I want it to go in a straight line down the right in between them. You see what I'm saying? Right in between the plates, right there. Okay. So to do that, I asked the question: what should the intensity of the electric or the magnetic field be in order for me to accomplish that? Well, let's see. So in order to get equilibrium, F sub E equals to F sub B. So what's F sub E? Well, F sub E is just Coulomb's law. QE, Q here, of course, is the charge on the moving particle. And F sub B is basically what? QVB. Of course, everything is perpendicular here. Sine theta is sine 90. That's equal to 1. So basically you get that. Look at that. So the charges cancel out. And I end up with E equals VB. This is a very interesting relationship that we will come back to when we cover electromagnetic waves. It will come out automatically again. So the condition for equilibrium, or the condition for the electric force, Coulombic law, and the magnetic force to be equal, is that when E is equal to VB. Okay, this is a very, very interesting relationship. So in light of all of that, that's all you need to know about velocity selector, really. And there is more to it than that, but that's all you need to know as far as this course is concerned. Is that for a velocity selector, when you read that term, think E equal VB. Okay, and how do we get that? We get it by equating the Coulombic force with the magnetic force, and then you solve, and then you'll end up with this very interesting relationship. Okay. Okay, cool. Back to the problem now. I hope with this the problem will appear to be a little bit easier for you. So problem number 11. Okay, so he says here, velocity selector having uniform perpendicular electric and magnetic field. Fine, okay, we got that so far. Here is the velocity selector, right? So, and then you got this velocity, the particle moving, so it's going to go through it here, and we're going to fine tune it in such a way that we want this particle to go right in the middle, okay? He gives you the distance between the plates, right in the middle, right here, okay? So he said the electric field is provided. Okay, so we have some information. The voltage on the battery is 150, and then we have the separated by 4.5 centimeter. He asking what must be the magnitude what must be the magnitude of the magnetic field. Basically, he wants B. Okay, magnitude of B, so that the charge is having a velocity of that perpendicular to the field past blah 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 blah. Okay, well, how do we do it? You can pause the video and think about it. It's not much to really to think about. Basically, he's asking to use this formula right there. So basically, he's saying B equals E over V. He gives me the V. Okay, he gives me the V. The V is, there we go. I mean, it's not the right unit, but there it is. 3.25 kilometer per second. So that will be 3.25 times 10 to the third meter per second. Okay, I got that. Okay, I got this V. Now I need to get E. Well, how do I get E? He didn't give me E, did he? No, he did not. But he gave me something that I'm familiar with from previous chapters. He gives me the voltage, and he gives me the separation distance. You remember that? So he said the voltage is, what? I forgot. 150. And the separation distance, let's call it D, equal 4.5 centimeter. Okay? Remember E? How is E is related to that? V equals ED. Remember that? Yes? Good. So E is equal to V over D. See what I'm saying? So we have 150 divided by 4.5 times 10 to the negative 2. And then I just calculate it. I have my calculator. I hope you're calculating with me. So I have here 150 divided by 4.5 E negative 2. Answer 3333. I hope I did it right. Newton per coulomb or volt per meter, whatever you want. And there we go. I have that. Okay. So now he said, what is the magnitude of the magnetic field? Well, B is equal to E over V. So that makes it 3.3 divided by velocity. He said it's 3.25 times 10 to the third. And when you calculate that, 3333.3 divided by 3.25 exponential 3. Answer 1.02 Tesla. Okay, there we go. I got the magnitude of the magnetic field. Okay, that's part A. Part B. Show how the magnetic field should point in the region between the plates. I'm just going to give you the answer. Like I said, unfortunately, I can't show you the right-hand rule, but I'm going to show you the answer, and then you can prove it to yourself once you work it out, once you learn how to do that. So it can look something like that. If this is positive, and of course the velocity It's going that way. So the electric field, now here I can show you something. Look, because look at the battery, look at the polarity of the battery. This terminal right here is positive, and this terminal is negative. So logically, this terminal here is going to be negative, and this one is positive, correct? Yes? Let me make it big so you can see it better. There we go. That's better. There we go. Look, this is the battery. This shorter line is negative, so this terminal must be negative. And this one is positive, so that means this one is positive. So what's the direction of the electric field, guys? It's going to go from positive to negative, so it's going to go up this way, correct? Up this way, up this way. Make sense? So now, if I'm going to draw it, you know what? Let me draw it with the selector. So here is my selector right there. So this is positive. This is negative. So here's my electric field. Electric field, okay? There we go. Now, what about the magnetic field? Well, if the particle, here's the particle, and it's moving in this direction, remember, V, E, and B must be mutually perpendicular, right? So if it's positive, what is the direction? What's the direction of the coulombic force on it? Well, the particle wants to go to the negative terminal. That means let me change the color. I'll put it to red or pink, whatever. So the particle want to go to the negative this way. So that's the force coulombic, electric, right there. So the magnetic have to be that way, for sure. And it's equal. Remember, it's a velocity selector. Fe and Fb are equal. So the magnetic force have to be in that direction. Well, how am I going to get that field to be in that direction? The only way that I'm going to get it in that direction is that, again, using the right-hand rule, and I wish I could show you my hand, but it's going to be out of the page, like that. Dot means out of the page, right? There we go. So it's going to be out of the page. Use the right-hand rule for out of the page, and you'll discover that it's got to be out of the page. So B here is out of the page. Got it? Okay. See, it's not that bad, is it? All right, one more problem. Yeah, number 18, kind of. Yeah, 18 is good. These are all homework problems. All right, let's go to it. Oh, right here. Okay. It's this diagram here. Okay. It says an electron at a point A, right here, has a speed V0 of 1.41 times 10 to the 6 meter per second. Okay. Shall I magnify it a little bit? Oops, not this one. Sorry. Okay. Okay, so here it is. So we have an electron moving in this direction, the green arrow, with a velocity 1.41 million meter per second. Question, find the magnitude and direction of the magnetic field that will cause the electron to follow a semicircular path from A to B. You know, something similar to what we have just talked about, you know, the mass spectroscopy, something similar to that. So you want to know the magnetic field intensifying the magnetic field in the direction of the magnetic field intensity. Okay, good. And B, the time required for the electron to move from A to B. And C, what magnetic field would be needed if the particle was a proton. I'll have you do part C. Part C is identical to A and B if you know that, understand them, so you just replace it with a proton. So you can do that. All right, how do we do it? Let me draw the picture. Always draw the picture. Always. Okay, so what I have in here, I have something like this. I'm going to turn it into X and Y, something like that, so it just makes it easier for me to think about it. And here is the electron right there. And here is the semicircular path that the electron is going to follow right there. From A to B. That's B right here. And that's a semicircular path. And then the velocity of the electron is given to me. V naught is equal to 1.41 times 10 to the 6 meter per second. And he wants part A. He wants the magnitude of the magnetic field. Okay? Well, this looks like mass spectroscopy, right? And if you remember, I don't need to go through back. If you go back to the notes, if you've been taking notes since the beginning of the video, we said that the magnetic field B, no, what did we say? Let's say M. The mass of the particle is QBr over V, correct? Go back to the notes and look at that formula. Okay? We're not interested in the mass. He wants B. So let's solve for B here. So B is equal to mv over qr. Is that right? There we go. That's the formula I need. Okay? How do I know? Because he said the electron is moving in a semicircular path. Well, that's, just like mass spectroscopy. So basically, it's telling me to use this formula. Okay? All right. So how do we do it? Let's go back and look at the data that we have. So here we have, he gives me the velocity. Oh, there we go. I was wondering what the radius is. There we go. He said the diameter of that circle is 10 centimeters. So that means the radius is 5. And so the diameter, 2r, is 10 centimeters. So the radius is equal to 5 centimeter, which is 5 times 10 to the negative 2 meters. Is that right? Okay. What else do we have? I think we got everything. Because for the electron, it's just going to be the mass of the electron, velocity given to me, V naught, over the fundamental charge times the radius. I have everything, so I can just plug it in. So B in this case is going to be equal to mass of the electron, 9.11 times 10 to the negative 31. I'm sure you've memorized it by now. We've done it so many times. 1.41 times 10 to the power of 6 for the velocity, divided by fundamental charge, 1.602 times 10 to the negative 19. Sorry, I'm working a little fast. Not good. There we go. Times the radius, which is 0.05, correct? And then we calculate that. I get an answer of 1.61 times 10 to the negative 4 Tesla. Okay, there we go. So the intensity of the magnetic field is equal to that. Okay. The second part of the problem, let me squeeze it in here. He says, the time required for the electron to move from A to B. Well, what is he asking for? The period, right? The time to complete one cycle is the period. Okay, let's talk about the period first. The period, tau, is what? Time to complete one cycle, correct? One circle for our case. Okay, so on that tau, how do I calculate that? Let me tell you something else. Hold on. Before I give you that tau. I'm trying to erase it. There we go. Look. How fast something is going around the circle? Well, it's equal to the circumference, 2 pi r, over the period. We talked about that before. Is that right? So the period in this case is 2 pi r over the velocity. Okay. However, what's the difference between this formula and the application or the diagram here? Well, we don't have a full circle. We have a half a circle. So what do? You basically multiply this by half. Make sense? So when I do that, that will give me the time to complete half a circle, not full circle. So basically tau, the time, is pi r over v. Okay? And we just plug it in. I got everything. I got pi, r is 0.05, divided by v. It gives it to me. What is it? 1.41 times 10 to the 6. You calculate that, and you will get 1.11 times 10 to the negative 7 seconds. Check my work, and there we go. Okay. Now you can also do the same thing for the proton, part C. Really the same thing, except that you have the same fundamental charge, but you have a different mass. And of course, because it's a proton, for the electron, because it's a negative charge, the right-hand rule applies, but it's opposite. Okay. In other words, for the electron, the magnetic field is going to be into the page, and for the proton, this is for the electron. And for the proton, it's going to be out of the page. Again, please convince yourself that's the main difference between them. Okay, so that's for it's out of the magnetic fields have to be out of the page, where for the electron it has to be into the page. Okay. Okay, good. Let me do one more problem, and then we will stop here. And I want to do something about that has to do with the current carrying wire in a magnetic field. I'm trying to find which homework problem. I mean, oh, number 74. That's actually a homework. Is that 74 or 75? I have a, yeah, 74. Let's do 74. That'd be cool. Let's go to 74. That's a homework problem as well. Page, let me find it here. Oh, I remember this one. Yeah. Magnetic balance, 74. Page 667. Okay. Right there, okay? You got to read a lot to kind of I'm trying to get it right in the center of the page. Right there. Okay, let's read it together. Here we go. As I read, you want to look at the picture right here. It says the magnetic balance. The circuit shown in this figure is used to make a magnetic balance to weigh objects, okay? The mass M right here, this is what you are weighing. The mass M to be measured is hung from the center of the bar right here, which is in the uniform magnetic field of 1.5 Tesla. Okay, so you have a magnetic field into the page. You see those blue crosses? That's magnetic field into the page, directed into the plane of the figure. Okay. The battery voltage can be adjusted. Okay, so you can adjust the battery voltage to vary the current in the circuit. Okay, so I can vary the current in the circuit. Why do I need to do that? All right, the horizontal bar is 60 centimeters long. That's the length of the bar, and is made of extremely lightweight material, so its mass can be ignored. Got it? So we're going to ignore the mass of the bar. It is connected to the battery by thin vertical wire that can support no appreciable tension. Okay, as you can see, he babbles a lot. All the weight of the mass M is supported by the magnetic force on the bar, basically. So basically what he's saying, ignore the mass of the bar, ignore the battery, ignore the mass of the wires, all of that, just ignore them. Okay, fine. Okay. Now, a 5 ohm resistor is in series with the bar, and the resistance of the rest of the circuit is negligible. Okay. I'm trying to get to the question. Okay, he said, which point A or B should be the positive terminal of the battery? Interesting. B. If the maximum terminal voltage in the battery is 175, what is the greatest mass M that this instrument can measure? Okay? Now, I urge you, stop the video and think about it, try to digest it, read the problem maybe a couple of times, just, make sure that you really, really understand it. Okay? So, again, this also has to do with the right-hand rule. I'm sorry, I feel bad that I can't show it to you, but that really has to do with the right-hand rule as well. Now, in order for, okay, here's how the situation works. Let me go back. Maybe I'll put this on the side so we can see it maybe. Try not to put it away from the edge of the video screen. Right there, probably the maximum I can put it. Nope, not this one. Maybe. Sorry, bear with me. You know what? I'll just leave it the way it is. There we go. Okay. Let's see how we do this problem. Let me draw it first. Again, I have to draw it. So what you have here is the battery right here. It's unknown polarity. You see what I'm saying? Here is the bar. Here's the bar. Big thick bar like that. I'll make it big thick bar. It's not supposed to be really. And here is the resistor, and there is the wire again. Wrong picture. Sorry. There we go. That's better. All right, that's the battery right here, guys. Okay, and it's from A to B. So this is A, and this is B. And then he said that the magnetic field is into the page. Is that right? And then you get the mass. Here is the mass right here, the block right here. This is the mass right here. Okay, so here is the mg. Okay, I want the magnetic field force to be opposite of it because I want it to balance. So in order for me to have it balanced like that, and I know that F equals ILB, right? Sine theta, but theta here is 90 degrees, so we can ignore it. So, and B here, look at that. B is into the page. Which direction I should be in order for it to be, in order for F sub B to be above, up, okay? And the answer for that is that it has to be this way. Again, use the right-hand rule. Like this, I will be this way. Yeah, I shouldn't have done that. There we go. It has to be this way. This way, there we go. Not coming out of it. So the current have to be in this direction. In other words, the current have to go into the counterclockwise position. Well, in order for the current to go in the counterclockwise position, what is the polarity of the battery? Where is the plus and where is the minus? Go back to, we covered that, previous chapters. What's the direction of the current here, guys? It's this way. Why? Because this is minus and plus. What about this one? The current is this way because from minus to plus. Now look at the current. The current is going this way. So that means from minus to plus, where is the minus? The minus have to be here, and the plus have to be here. Make sense? So now, answering the question, go back to the question as he's asking. He said, which point A or B should be the positive terminal? Well, it's A. Make sense? Okay. The second part, he said, if the maximum terminal voltage on the battery is 175, okay, that's the maximum voltage there, okay, what's the greatest mass that you can measure? Okay, so basically what he's asking for really is balance the magnetic force with the weight. Just make them equal, okay? Have you noticed that you always make things equal? So just make them equal. So that basically sum of the forces equals 0, if I'm going to write it correctly, properly. So in this case, F sub B is equal to mg. So that's ILB equals to mg. And he wants what? If the maximum total, what is the greatest mass? So he wants to solve for m. Okay. So m in this case, let me solve for it. I like to do the algebra before I put in my numbers. So it's going to be ILB over g. Okay. Do I have everything? What do I have? Let's go back. I have here, there we go. I have B. He said B is 1.5 Tesla. Let me write it down here. Do I have L? Yes, I do. He said the length of the rod. There we go. He said the horizontal bar is 60 centimeters. So I know the length. So the horizontal bar is 60 centimeters. So I got that. I got that. And of course, G is 9.8. That's easy. And what's left is I. Well, he gave me some information just to make it, sound harder. He said the resistance is that and the voltage is that. Well, does this ring any bell? Ohm's law, V equals IR. That's why he gave them to you. So I can find I. So therefore, V equals IR. So therefore, I is equal to V over R. I don't need to plug it in. I can plug it in and get the number if I want to. Or I can just take this one and put it right here. So in this case, the mass is going to be equal to V L B over R G. You see that? Plug it in. You're done. That's it. It's really that simple. So, you have 175 times 0.6 for the length of the rod. B is 1.5 divided by the resistance. He said is 5 ohm times 9.8, and then you calculate all of that. Let me calculate it for you. 175 times 0.6 times 1.5 divided by 5 times 9.8. Answer. The maximum mass, this is maximum. You see what I'm saying? Whoops. The maximum mass is 3.21 kilogram. I hope I didn't do it wrong, the calculation. And there we go. Okay? All right, I think I'm going to stop here. I may do a couple more next time. You're more than welcome to, I'm going to do the second video probably in a couple of days. So in between, if you happen to read or to read the material that we have covered, you're welcome to tell me, do a specific problem for you. I'll be more than happy to do it, okay? In the video, that is, okay? So anyway, I'm going to stop here, and I'll talk to you soon. Bye.